All right, so I'm not going to go through the details of how you do the backwards induction. That's in the handout. The main idea is beautiful. Sometimes it's easier to prove certain versions, certain values than others, and you prove those first. It turns out it's much easier to prove powers of 2. And once you have powers of 2, you do a special filling in to get the remaining stuff and fall back downwards. So it's a really nice backwards induction. What I thought I would do today is try to use some of the techniques we've done to do a problem that somebody had emailed me about. One of the nice things about this class is I don't have to know how to solve the problems. And so I will admit I do not know how to solve this problem. I have deliberately not tried to solve this problem. Okay? It's one of the joys of teaching this. And the difficulty, though, is I have to prepare enough so that I think we can solve the problem in class. Or if not solve it, at least get to an interesting, good place. So I hope I have at least done that part well. And so the problem is the following. Okay. Given a unit sphere, because really, who would consider a sphere that's not unit, right? Right? God would, or just saying, oh, God?
Yeah, oh, God.
Oh, God, yeah, I mean, exactly. I mean, all spheres are unit spheres, right? Given a unit sphere, consider n, say, closed hemispheres, H1, Hn, such that each is a subset of S, and S is contained in the union k goes from 1 to n of Hn. All right? So what I'm saying is I take the unit sphere and I consider a bunch of hemispheres, or just cut it in half. And I'm going to assume that my hemispheres are chosen in such a way that their union covers the entire original sphere. What is the minimum number that n has to be? What's the smallest we can do? 2. Is it easy or hard to do it with 2? Okay, in some sense it's easy. Just take North Pole, South Pole as your centers. If I were to choose 2 hemispheres at random, likely or unlikely that it will work? Extremely unlikely. What about 3, 4, 331, 2014? Do you think it becomes easier or harder? So that if you just choose a bunch of points at random, you'll cover the whole sphere. Yeah, I mean, it shouldn't get harder as you choose more hemispheres, right? The more hemispheres you have, the greater chance you have of covering everything. But in a lot of problems like this, it's not find a special set of points. It's we're given a set of points that cover. And here's the claim. Always have S covered by 4 of these hemispheres. And I'll say if n is greater than or equal to 4, because if n is not greater than or equal to 4, then we don't have 4 spheres to play with. So somebody had sent me this problem. If I am not remembering this problem correctly, please correct me right now. But OK, good. I'm seeing the finger go up. Good. So here's the problem. So let's spend a few moments and just brainstorm how should we attack this. Here's a problem which some of you may have looked at. I know at least one of you has looked at. I've looked at it a little bit. How would you tackle this? What are your thoughts?
Well, the sphere is the gluing of 2 hemispheres. Maybe we could tackle the case of a circle being,
Excellent.
Being the gluing of 2 lines along their boundary.
OK, so what do you mean by that?
I mean, you take 2 disks along their boundary, you get a sphere. If you take 2 lines and glue them along their boundary, which is the endpoints, sort of in a similar way, you get a circle.
All right, so you're basically doing some kind of topological thing and building up?
Yeah, maybe inducting on dimension.
OK. So I like the idea of inducting on dimension. So rather than directly tackling this problem, whenever you get a problem, you always want to ask which numbers matter. So what numbers matter? In a problem, if you see 2014, does 2014 matter? Probably not. One of the reasons I wanted to do the chessboard problem early in the semester was the dimension of the chessboard being 8 by 8 actually mattered. It was important that 8 was a power of 2. But all that mattered was 8 was a power of 2. So for a lot of problems, sometimes the numbers matter weakly. And you want to get a sense of when do things matter and how much do they matter. So over here, what numbers matter? Well, what numbers do we have? We have n. We have 3 dimensions. And we have 4. Which do you think is the key number that drives all other numbers? So which is the key number? Yes.
4.
Why 4?
Because, well, first of all, that would define how large, well, given how much we can accept from n, and also in the case of 3 dimensions, it doesn't really matter, right? We can extend this problem to something else in 2-dimensional.
Well, do you think if I change the problem to 7 dimensions that it's still going to be a 4 here? Which number do you think controls the other numbers? Now, of course, you could look at it many different ways. As I change this number here, that would then change the dimension. So one way is to look at it as, I want to show that if I have a covering of n half objects, if my dimension is at least blah, then I have a subcover. I think it's more natural to look the other way. You can look at it this way to say, let's look at d dimensions. I have n half objects in d dimensions, and I claim that there's some number that suffices. And try to figure out how do these numbers depend on d, on the dimensions. So I really want to view this as a function of the dimension. Yes?
I'm just a little confused about the actual problem.
Okay.
This is a little late, but
No.
So you're saying that if we have, n hemisphere inside this unit sphere,
Right.
then if we have at least 4, then we'll always cover it. The union will always cover
No.
it.
If you have a sphere
Yeah.
which is covered by n hemispheres, and n is at least 4, it's possible to choose just 4 of the hemispheres and cover everything. You don't need all n. That some of the hemispheres are redundant. So imagine I have 2014 hemispheres such that their union is the unit sphere. I can find there's at least one set of 4 special hemispheres that would cover everything.
Okay, that makes sense. Thank you.
Okay, yep. Did you ever?
So the S in question here is the sphere itself.
Is the sphere itself.
Okay.
Yes. Okay, so given a unit sphere S. Question?
If we're just concerned with the surface of the sphere, then isn't it 2-dimensional?
It's 2-dimensional, lives in a 3-dimensional space. You're absolutely correct that we have some flexibility in terms of how we choose to view the dimension. Are we talking about the dimension of the boundary, or are we talking about the dimension of the ambient space it lives in? It's not going to make a huge difference one way or the other, because there's going to be a very simple relation between them. They differ by 1. Was there a question from over here? No. So we have 1 data point. In a 3-dimensional ambient space, we need 4. So what do you expect we need in a 4-dimensional ambient space? Yeah, I mean, I see a couple of people going like this. I'm very hesitant to conjecture with just 1 data point, right? How many data points do you really want to have before you make a conjecture? Yes?
3.
At least 3 would be nice. At least 2 would be a minimum. How many of you have taken a stats class? In stats classes, you calculate means and you calculate standard deviations. If you have 1 observation of a population, can you estimate the mean?
You would assume that it's that.
You would use that value, right? So I estimate the mean from one observation. Can you estimate the fluctuations about the mean with one observation? No, right? And that's why if you look at stats books, they talk about dividing by not n, the number of data points, but n minus 1 for the sample standard deviation. You should not be able to estimate from one value. Over here, I'm very hesitant about making any conjectures. I could say, this is one more than that. I conjecture that the number you need is always one more than the dimension of the ambient space. If we went to what was suggested and say that this lives in a two-dimensional space, we would say, it's always double. Or maybe it's always the square. There's too much flexibility. There's too many functions you can fit with not enough data. So when you're trying to do a problem like this, there's lots of ways to attack it. In my mind, one good way to attack a lot of problems like this is to look at simpler cases. And so I think let's look at a two-dimensional case. Let's look at a one-dimensional case. One of them should be laughable. Which is the laughable case? One. So again, I go on this night show, I'm not going to get laughs, but I'm hoping here I will get laughs by looking at the one-dimensional case. Right? They got at least one laugh, right? Here's my sphere, 0, minus 1, 1. I have to cover it, right? And I'm covering it, well, what do my hemispheres, my one-dimensional hemispheres look like here? So in 3 dimensions, it's a hemisphere. In 2 dimensions, it's half a circle. What's it here?
It's half the line, and so you're going to have to cover each end of the line, and so you're going to have half a line at each end, so you can choose 2.
Yep. Or since I don't really care about the interior, if I only care about, say, the surface, I just have 2 points here. So if I'm going to cover it, how many points do I need to be guaranteed to cover? Or to have a chance to have a cover? How many points do I need? 2. And if I have a cover, once I have a cover, I will always have a subcover of just 2 things. So one dimension always have a subcover with 2 objects, if n is at least 2. Hey, what's the relationship between 2 and 1? 1 more. Do you feel a little bit more comfortable now that 4 is 3 plus 1? And of course, I mean that in this particular problem, we should view 4 as 3 plus 1, not that 4 is 1 more than 3. But look, now we have 2 data points. Nobody feel, okay, not much more comfort here. All right, let's look at the 2-dimensional case. And again, I don't particularly care about this problem, I care about the thought process. So I have a 2-dimensional problem, draw pictures. If possible, draw good pictures. Here is a circle, and I want to cover the circle. How many objects in my cover do you think I'm going to need? We may not have proved it yet, but does anybody have any thoughts?
3.
Maybe 3. Where can we always put one of the covers?
Bottom hemisphere.
Bottom hemisphere, top hemisphere, left, right. There's lots of canonical choices of where to put one of the covers. Doesn't really matter. We can always assume, we have a first one, if you want, down here like this. And now we want to see, imagine we have a cover. We want to figure out if we can cover the boundary of this unit disk with n half circles. We want to show that we can always do it with a subset of size 3. So there's lots of different ways we can be looking at this. Maybe we're going to be trying to induct on dimension, and this could be an induction on dimension. That might be overkill. Because then that's not only solving the original problem, it's solving a massive generalization of this problem to higher dimensions. Do you think an analog of this should be true in 4-dimensional space? Yes. Is that going to be pleasant or unpleasant to visualize? For most of us, unpleasant, right? And this is where algebra comes to the rescue. But there's probably a generalization of this to higher dimensions. It's much easier for me to work in lower dimensions and go in the other direction. They're starting us off in 3 dimensions. They've left 1 and 2 available for us to get some intuition as to what's going on. So let's try to look over here. So imagine we have a circle S, and it's contained in a unit of, we'll call it half circle 1, union half circle 2, union half circle n. And we want to show only need 3. Okay? So somehow we need to go through this and show that we don't need all of these. Is there any condition under which you would need all of them? So I have S's contained in this union. When might I need every single one?
So you have 3 and the other 2 are just like this.
Be more specific.
If your cover started out with 3 semicircles, and let's say you had 1 on the bottom, and then the other 2 just sort of go up the sides. And
Okay. So I could have something like this, plus this, plus this. I guess I should draw this a little bit higher. So in a case like this, I would need all 3. So I'm not expecting to be able to do it in just 2. Okay, so I would expect that, at the bare minimum, I'm going to need 3. And you could play other games. I could have it over here. I could rotate this one a little bit like that, rotate that one a little bit like that. You can start playing lots of different games. Yes?
This is maybe a dumb question.
Yep.
Why do you need 3 if you have 2 of them that cover the complete circle?
Well, I'm saying I don't know where they are. I'm just saying I have n half circles, and I'm told my whole circle is covered by the n half circles, but I don't know where they are. The question is, I claim that I don't need all n. I can always winnow down the set and throw a bunch of them away, and I only need to use 3 of them. I don't necessarily know which 3 I need.
I think what she meant is that
Okay.
the 2 semicircles on the right.
Oh, that these 2 ones over here.
Are they rotated?
So that these 2 ones, and I actually don't need that. Okay. Okay. So maybe I do, instead of this, maybe I do, well, that's a horrible circle, but so maybe I do things with maybe a third of an angle. Here's 0, something like that. And so now if I take this one over here, any 2 of them, I think, would not cover the whole thing. So what if I chose these points, 0 degrees, 120 degrees, 240 degrees? I get 90 degrees in each direction from each one of these, right? Do any 2 of them cover the whole thing? No, because if I go down from 120 by 90, I only get down to 30 degrees. If I go up by 90, I only go up to 330. I miss everything from 330 to 30 degrees. So 2 of them is not sufficient. So if I use this configuration, you're right, the initial configuration, I could have just gotten away with these 2.
So what you were doing is you're just saying
It can be 2, but actually,
No, it can't be 2.
it can't be 2, right. If I have this configuration, there's no way to do it with just 2 of them. So at a minimum, I'm going to need 3 in some cases. And the question is there some configuration that might force us to choose 4? Yes?
I mean, if each of the half circles is only 1 degree off each other.
But remember, you're then going all the way around. So you start off at 0, but if it goes off by 1 degree, when you get to around 180, 181 degrees, that's going to get you essentially all at the top.
Yeah, but then the next one's only shifted a little bit, and then the next one's only a little bit more. So it's
Right, but you don't know, but you're not saying ahead of time which ones you need. So take the one at 0 degrees and the one at 180 degrees. So wait. Right.
I think what you're saying is that like you're right that there's a couple of half circles if you pick them don't cover the whole circle, but we're always guaranteed a set of half circles that will cover
Right.
the whole thing.
We're saying that there is a set of 3 that works, not every set of 3 works. So you're right that if you do it by 1 degree increments, that most of the sets of 3 won't work. But if you take one down here and then wait a long time before you take another one so that you get all the way up towards the top, then you'll be in great shape. And then in something like that, you will be able to do with just 3. So for stuff like this, it's great to just play games and play configurations. Yes?
There's kind of a geometric proof applies on 3.
Okay.
So if you do something like that where you're continually kind of layering them on
Right.
top of each other to like a bunch of them,
Right.
and then you take another one and cover it, the rest of it, all the layered ones, besides the one that's the biggest, are contained within the biggest one and the original layer.
Good. So what you're saying is that you can collapse and you can remove a lot of them. But you've got to write this up very rigorously. And that's the difficulty. We're closer, I think, to the physics part of the building than the math part of the building, but we still have the math part of the building's proof standards. But you have the right idea that when you have something like this, you can basically say, look, anyone in between these two are not needed, and I can collapse them. So what we want to do is we want to take the set and we want to prune it. Because here's the claim, and again, this is why we'll probably spend the entire day discussing this one problem. There's a lot of good ideas behind this. We have S contained in this union. And the claim is that no matter what n is, as long as n is sufficiently large, you can always find a set of 3 that work. Well, what we're going to do then is we're going to say, fine, you give me a really large set of n, I'm going to throw away one of them. And it's still going to cover. And I'm going to throw away another one and throw another one. And you've just told me how to throw them away. If I have one center that's between 2 of them that's not too far apart, I don't need it. So that's the idea, is we want to find a way to prune our set so that we only go down to just 3 things. And then we'll have 3 things that are in some sense separated.
Well, maybe just we could just project the top of the circle down to a straight line so we can talk about leftness and rightness geometrically.
We could do something along those lines and try to look and see where we are. We have the first one over here.
Yeah, something like the rightmost endpoint with the tail circle to the left of it and the leftmost endpoint.
And when we do some kinds of projections, we're going to have maybe certain repeats on one side or the other. Okay, there was another comment from the class, or? Okay, so I want to put in a lemma that I found useful in thinking about this, in terms of helping out which ones I need. So imagine I have S contained in this union. There is a trivial condition that tells you when you are not allowed to throw away one of the sets. A trivial condition that tells you you must keep this as one of your sets. What is that trivial condition? Yes?
If it covers some area of the circle and none of the others.
Good. If it has one point that's not in anything else. So imagine you have an H such that every point in H is contained in some other H. Do you need it? No, you can throw it away. So it's enough to just consider the cases when no H has a point that is in nothing else, at least if n is large. So I want to somehow start to winnow things down. So it's, how do we write this clearly? So, all right, so imagine n is big and h1, h2, ... hn all have a point only in them. Then no winnowing is possible, of our list is possible. And I claim that this is going to give us a severe restriction on n. So let's think about what's going on. I have my sets h1 through hn. Each one has some point that's not in any of the other h's. If everything in hn was in something else, I could just drop it and try to do the problem with one smaller n. Okay, so let's start off on the unit circle. And we'll put our first point over here. And that gets us all the way in through here. So the next set has to have a point. How far away does that point have to be from P1? So here's H1. Now I'm going to put in P2 somewhere. How far away does P2 have to be from P1? Yes?
If we're talking about degrees, it would have to be like just greater than 90 degrees away.
It has to be at least 90 degrees away. So P2 has to be somewhere over here.
Like, why does P1 have to be there in the middle? Like, why can't it be like, if like the...
Oh, because I can always just rotate my circle to put P1 on the boundary. I mean, on the bottom.
Well, what I'm saying is that like, if like your cover is like the bottom half, like why does P1 have to be in the middle? Like, why couldn't it be like next?
Well, I'm sorry. No, oh. Okay, I'm not saying that P1. Thank you. I'm not saying P1 is the point that is only in H1. I'm saying P1 is the center. Thank you. P1 is the center of H1, and so the center of H2 has to be. Does it have to be at least a certain distance away from P1? Yes.
Sorry, what condition are we trying to satisfy here in replacing the P9s?
So I want to try to get points. Okay, well, let's see. So let's imagine we have 4 points. I think you're right. I think the way I'm writing it up is not a good way. Let's say we have 4 points, P1, P2, P3, P4. And none of these points can be in any other half circle. So how close could P3 be to P2?
Infinitesimally about 90 degrees.
Well, a lot of it depends, unfortunately, on where the centers are of these. And this is where things can be tricky. Yes?
I was thinking of it as like given 2 points, like say P2 and P4,
Right?
as long as they're closer than 180 degrees together, then anything between them can be thrown out.
Okay.
But like given just 1 point, I don't know how you can make those out where the next one has to be.
So we could do that for winnowing and then say that given, if we have 2 points whose centers are at most 180 apart, we don't need anything between them. And then we have our string of centers and we would throw them all away. So I love that approach. I think that approach will solve the problem very quickly. I want to see if this can be salvaged or if this goes on the scrap bin. So your approach will definitely work, and that goes back to what you were saying in terms of we can throw away a bunch of things as not being needed. So here I wanted to say that we have to move at least a certain distance. And so, if I have, 2 different half circles, how far apart can their centers be? If their centers are too close, am I going to have problems? It's which points am I getting? So I don't know where the centers are, and this is what's showing us that maybe this is not the right way to attack the problem. Because now I'm starting to worry about where am I going to be putting my centers. Is my center here? Is my other center here? Is it on this side? And you can start to see the number of cases is just growing astronomically. Whereas the other approach was, well, look, I have a bunch of centers, C1, C2, C3, CL, CL plus 1, CN. And whenever 2 things are within 180 degrees of each other, this gives you 90 in that direction, this gives you 90 in that direction. None of the stuff in between are needed. And so we can now drop all of the stuff over here and decrease our n. And so we can keep doing that so that when we are done, we can then make some assumptions about how far apart the centers are. That if we start off with C1, the next center has to be at least 180 from it. But of course, if it's more than 180 from it, it's less, so we'll be careful in terms of which direction we're going. And we'll say that there's nothing. So we've got to be very, very careful. So you want to amalgamate things. So we'll have maybe CL, if it exists, is less than 180. Yes?
Couldn't you just go in both directions?
You can go in both directions. You want to talk about.
At the same time, just like in general.
So what you want to do is you want to start and say, well, look, I start off with C1. I look at C2. Its center is either less than 180 in this direction or less than 180 in the other direction. In one of the ways in which I move, I'm moving less than 180 degrees. And so I can just keep walking in this direction. And I'll walk at some point, and I can walk as far as CL and still be within 180. And if I do that, I no longer need any of these. And then this angular measurement is less than 180. And now we move in the other direction. And when we move in the other direction, we go some distance. And now when we start going in this direction, you will get to some point CM. And this will be less than 180. And now we can throw away all the stuff over here. We can throw away all the stuff over here. Could CM and CL be the same? The only way they could be the same is if it's exactly 180. So if I ever have 2 points that are antipodal, we're done. So if CM equals CL, we're done. So now we're starting to break into cases. Right? So the problem is if CM and CL are too far apart. But we've got to get stuff between. And so this is where it becomes a real pain as to how do you write up a problem like this.
How is that? How can they be farther? How can they be far apart?
Well,
Like if you're going as the maximum between 0 and 183, you're going to get to 2 points, right, that are.
okay, here's C1, C2, C3. Here's CL, CN, CN minus 1, CM.
But it has, so if you had just those centers, it
Right.
would,
Right, you would be missing something down here. So you've got to be able to, you've got to be doing some kind of argument to describe that you keep covering. This is where these problems can become annoying, in that it's clear what's going on, but to write it down carefully becomes quite painful. Yes?
Is there a way to require that CM and CL be more than 120 degrees away?
So if CM and CL,
Or more than 120 from C1?
okay, so how far do you want CM and CL to be?
I was thinking 120, but that could just be made up.
So you want it to be 120 to get from here to here? That leaves a large stretch in
yeah.
through here.
Yeah, I'm just trying to think that CM and CL are close enough to each other. That's all.
Well, we want CM and CL to be far from each other. Because, CM and C1 is covering this huge stretch over here. C1 to CL is covering this huge stretch to here.
Right.
But here, if CM and CL are close, we no longer need C1. And we can keep building.
Okay.
Right? So if CM and CL are within 180 of each other, we clearly don't need C1. So we can assume CM and CL are less than 180 from each other.
But we can't always assume that. In certain cases.
No, and this is where, in terms of writing this problem, it becomes a real pain. Yes?
Well, I guess want to do it by construction, right? Just say,
Okay.
okay, well, let's try to construct something that follows that.
Okay, so are we starting here? Are we going down like this and going down like that?
No, as in like, okay, so let's add one hemisphere.
Okay.
We know that has at least one unique point at like C1.
Okay, so let's start. We start off. We've added this down here. So we've added this hemisphere down here.
So now you add a second, any sort of second hemisphere that can overlap the first in any sort of way, with the exception of touching C1.
Or that contains one point that is not contained in the
Right, but the problem is, what if it's that small little point over there, and we now have all these whole sequences, and now we have to go through all this argument? We're close, but we're not there, because problems like this do not have long, tedious arguments. That's how you know you're not writing it the right way. These have an elegant way of phrasing it. And if we haven't found that elegant way of phrasing it, we're not looking at it exactly right. We're close. We know we have to have, some stuff up above. Yes?
So as the bringer of this problem,
Yes.
I feel obligated to share my proof, the 2 case.
Okay, good.
So should I?
Sure.
That's a good picture for it.
Do you talk about how you have to have 2 points up here?
No.
Okay. Okay.
Could I draw it?
Sure. Come on up. You just now have to realize that you're going to be recorded, and because I have the recording thing, I have to stand near you.
I accept.
Okay.
Yeah, so we start with one hemisphere and that's it's any point, or it's any one of the covers, or one of the hemispheres that you're using as a cover. And another hemisphere has to cover this midpoint of the remaining circle. So it has to look kind of like, this or this. But the point is it leaves like this wedge shape, which has like an angle smaller than pi over 4,
Mm-hmm.
or pi over 2. So we can just assume it looks like that. And then again, take the midpoint of this. Another hemisphere has to cover that, right? So notice that if the hemisphere kind of looks like this, or if it crosses, or if it doesn't cover the entire portion here, then it obviates one of the, like here, it makes this hemisphere unnecessary. And so you can continue like covering. And every time you're rejecting a hemisphere that you already have, so that you're like winnowing this space down until you have a very, very thin wedge that's not covered. And you can always do that with only 2 hemispheres. Like we're just choosing 2 hemispheres that cover everything but this section. And like the final hemisphere has to, well, you're assuming that this is like the smallest possible wedge that you can get. So the final hemisphere kind of just covers the entire thing. And you can either get that by, 2 hemispheres just looking like this and this, or the final hemisphere can kind of cover it like this. But you kind of see what I'm doing.
Yeah. But it still doesn't seem like it's phrased elegantly. Do you have an elegant way of phrasing it?
Yeah, so if you start with one hemisphere on the bottom, you choose another hemisphere that only intersects one point that's already in the other one, and then your third hemisphere just has to intersect one point from each.
You want to come up and try to draw it? So we start off, we've got the bottom.
Yeah.
Now what do we do?
And so you have the bottom.
Yep.
And so for your second hemisphere, you have to make sure that it only intersects one other. So it'd be like that. So it only touches at least one point that's taken up here. And then the other, our last hemisphere, just has to touch one point of each. So that would be like, well, that's not a hemisphere. But pretend they all intersect here.
I no longer feel bad about my artwork. But how do you know you've got these constructions and these points?
Well, because of the 90. What do you mean? If you have a certain number of hemispheres, don't you for sure have at least one hemisphere that touches our original hemisphere, that intersects our original hemisphere.
Mm-hmm.
And it has to intersect at least one point, but there could be a couple other hemispheres, and so, and your cup, can I just fix that? That's really bad. So this happens to intersect all here, but it's going to intersect at least one point, and you only need it to intersect at one point.
Okay. Again, I think all of these arguments are essentially there, but yes.
I think we could maybe use our inductive hypothesis.
Okay.
Do this as a problem on a line.
Well, I was thinking, let's start off with the first hemisphere, which everybody's been drawing. And now what we can do is we can say, let's look at the point at a center over here, which is furthest from here possible, and still in this quadrant. So I start off, I choose this as my center 1. I have to get all of these points. So I want to have some hemisphere, or some semicircle, that covers these points. So it's got to have a center somewhere. And so the question is, where can I put the center? And if I put the center, C2 all the way up into here, I want to see what's the highest I can go for C2 and still cover points in here. And so I can cover every single one of these points. Yes?
So the highest you can go is 180, and the lowest you can go is 90 to still cover that.
Right. And so you give me any point in here, and I can cover it somehow. So for instance, if I take this point over here, I've got to be able to cover it. And so where could my centers be to cover it? The centers could be all the way down from here, down to here, or all the way up into here. And so I've got to choose a value of C2 somewhere in this section over here. And I want to see maybe some kind of maximality, see how far I can push along these lines using this idea we've had multiple times of things being amalgamated. Yes?
What guarantees that we have hemisphere in the layer?
Well, we know that this point is covered. So there's got to be some semicircle that covers that point. The question is just, where is its center? And so in order to cover that, the center can't be more than 90 degrees from it. So it's got to be somewhere in this window. And so I want to somehow get some kind of maximality. Imagine, the other possibility is, imagine we had no centers anywhere in the top. If we had no centers anywhere in the top, what would happen?
It wouldn't be a valid set.
It wouldn't be a valid set. So there's got to be a center somewhere in the top. Does that help us? So we know we get all the bottom down here. We know we have to have a center somewhere in the top. So we have a center somewhere in the top over here. That would give us something like that. And now we need to get something like this. And we would know the angular measurement of there can't be too large. So is this enough? The difficulty is now, maybe this is covered by a point that's very close to over here, and I'm not covering over there. But because I have so much of an overlap over here, I should be able to shift down here at the cost of moving that. We're basically saying the same idea again and again and again. I don't think we've yet hit the nice, elegant way of phrasing it. To me, it's the fact that we're moving by 90 degrees. We've got to move by a little bit more than 90 degrees. I can do it 3 times and get 270. I can't do it 4 times. And so, if I look at points, can I find 3 points so that the angular measurements are what I want? That the first one is somewhere between 0 and 90. The next one is 0 and 90 from that. The next one is 0 and 90 from that. And then that's less than 90 from the last one. Well, if I'm moving too small, no. So I've got to be moving large amounts. I've got to have a couple places where I'm moving a good amount. So over here, if I have a wedge over here, this wedge over there is going to have the same girth. And I should be able to start slowly moving some points over here. Are there any centers in this range? If there are no centers in this range, what would that mean if there's no centers in that range? I've got to have centers coming from over here or centers coming from over here. And so I'd have to have maybe something over here, 2 points like that. So it's a problem if I have a region where I don't have any centers. So I think this is a great problem. I think there's a lot of wonderful ways of trying to look at this. I'm not convinced by anything either I have said or you have said of an.
Okay.
Yes.
So 2 hemispheres exclude something that looks like a sector of the circle.
2 hemispheres exclude a sector. So we have an excluded sector.
Choose 2 hemispheres that exclude the sector with minimum area.
Ah, I love that now. Okay. Choose 2 hemispheres, hemicircles, that exclude minimal sector. I love that phrase, minimal sector. Okay.
And then the sector can't be contained partially in a hemisphere. It has to be contained completely within one hemisphere.
So why does that have to be contained completely within one hemisphere?
Well, if you draw another hemisphere through it, then, like that only contained partially, then those 2 hemispheres will contain one hemisphere.
So what you would be saying then is if we have part of it, I would then lose some of the stuff over here, and I would have something smaller. That's the first one I've heard that's really convincing. This kind of minimality principle. And so we choose the 2 hemicircles that exclude the minimal possible sector. I've got to contain this somehow. So there's got to be some, you have the point over here, I've got to have something that contains it. And so it's got to have a center either up top or down below. It will overlap with this one, but overlap less. So choose that exclude the minimal sector, need to cover, if not all in a hemicircle, violate minimality. And that will then give us that we can do it in just 3. And just before the bell rings. All right. Is that convincing? This seems far different than the arguments we were making in terms of just the phrasing and how clean it is to phrase it. This is one of the key proof techniques, this kind of minimal configuration. I still feel that there is a way to do everything we've been talking about, expanding, coming upward. I would love for somebody to write that up cleanly. I feel like there should be some way of looking at 4 points and their distances have to be a certain amount. There should be some way of writing that cleanly. But you see how long and involved it's getting. In one of my classes at Yale, after writing 2 pages of long brute force computations, I wrote on my exam book, there must be a better way of doing this. And the professor wrote in the margins, it's about time you realize that, Steve. And he was right to put that down. I should have realized that on an exam there's a better way of doing it. In all problems like this, unlike life, there is an elegant, simple way of looking at things. And if you find it, the problem is much nicer. So here, I like the idea that we have a minimal excluded sector. And if this is entirely contained in something else, we win. Okay. The other idea was to start winnowing our set down to just 3 and then show that somehow if you have 3 things, you've got to cover everything. So imagine now you have 3 things that cover. Can you somehow get a subcover from that? I'm sorry, you have 3 things that cover. Okay, you're okay. So can you somehow make the argument along those lines? So I think this is a good place to stop as in we've run out of time. But what I want you to get from this is bringing the problem down a dimension, trying to build up. How many of you are now confident that in dimension D you need D plus 1? We showed in 1 dimension we needed 2 things, in 2 dimensions we need 3 things. The problem is in 3 dimensions we need 4 things. To me it's now really looking like you need 1 more than the dimension. Can you somehow generalize an argument like this? The geometry becomes much harder. So I think this problem is worth looking at